All right, this is Mr. Gillum, and today we're going to learn about parallelograms. They're a type of quadrilateral, meaning they're a type of four-sided figure. For a quadrilateral to be classified as a parallelogram, what has to happen is they have to have two pairs of opposite sides that are parallel. Okay, so they have to have two sets of parallel lines. I also want to emphasize that the abbreviation for parallelogram looks like this. So parallelogram A, B, C, D. Sometimes they're more emphasized, they look more straight up and down. I like to make sure I have these nice slanted lines, set of parallel lines there when I'm labeling mine. But not all quadrilaterals are parallelograms. For instance, a trapezoid would not be a parallelogram because they have four sides, but they only have one set of parallel sides. Okay, so it'd be considered a trapezoid. So parallelograms are a special type of quadrilateral. Okay, if we have a quadrilateral that's a parallelogram, then the opposite sides are congruent. Okay, so not only are they parallel, but they're also congruent. So that's important as well. So the most common example would be like a rectangle. If we just had a rectangle and these are all right angles in here, we would know that this side and this side are of equal length, and so are these two opposite sides. Okay, we also know in a rectangle that it also has two pairs of parallel sides as well. So in a parallelogram, this rectangle is just like, it's just tilted sideways. So now we just have a slant. The lengths are still the same on the opposite sides. So a parallelogram, the first theorem we should be familiar with is that it has two sets of congruent sides that are opposite from one another. Okay, so if this is a parallelogram, not only does it have opposite congruent sides, it also has two sets of parallel lines. So if we're considering this a parallelogram, this would be two sets of parallel sides as well as two sets of opposite sides that are congruent. So let's take a look at this next theorem about parallelograms. And what the theorem says is that opposite angles are congruent. So when I say opposite angles, I'm talking about like angle M and angle K. Those are opposites, or angle J and angle L. They are congruent. Now we know this, and we're going to actually prove it later, but we know this because, and it's easy to remember, if I continued these auxiliary lines, I just kind of extended those parallel lines, because after all, parallelograms are made of parallel lines, I would know that this angle is congruent to this angle because I know that this guy right here is alternate interior to this guy right here. And this guy is corresponding to this guy. So I can go through the motions, and I just informally just told you the proof that you're going to have to do here tomorrow or the next day. But I know that these opposites must be congruent because of these parallel lines. Okay, so opposite angles are congruent. That's important as well. Another theorem that we can talk about is the consecutive angles are supplementary. Okay, so again, this is stuff that we've talked about for a while now, and it had to do with the parallel lines. And we talked about, all the different relationships in triangles with these parallel lines. But now we're going to actually apply that to quadrilaterals. So if I made these auxiliary lines again, these are parallel because we are talking about a parallelogram. I know that these are consecutive interior angles, y and x they are. So I would know that x plus y would equal 180. And so that's going to be another, just one of those things that we've talked about it before, but now we have a specific theorem about a specific shape called a parallelogram. We know that its consecutive angles are supplementary. And finally, if a parallelogram has one right angle, then it has four right angles. And similarly to all the other parallel line theorems that we already know, if I continue this, because it does say that in the directions it is a parallelogram, I'm going to go ahead and mark that those are parallel to one another. If this is 90 and its consecutive angle would be, I have to add up to 180, then that would also have to be 90. Again, if I was looking at these parallel lines, the consecutive angles would be these two right here. Those are consecutive interior angles. That would have to be 90. And finally, it's quadrilateral. The total amount of degrees in a quadrilateral is 360. So if I already had three 90-degree angles, the last one would also have to be 90 degrees. So basically, these theorems are things we already know, but we're making them specific to parallelograms. All right. So let's take a look at this one. It says in parallelogram ABCD, suppose that measure angle A is 55. Go ahead and mark that right now so I don't forget. A is 55 degrees, AB is 2.5 feet, and BC equals 1 foot. Okay, find each measure. So the first measure we're going to be looking for is DC. And one of the theorems we know that is if this is a parallelogram, then DC must be congruent to AB. So because I know that this is congruent to this guy, and I know that that guy is 2.5, then DC must also equal 2.5 feet. If I'm looking for measure angle B, which is this little guy right here, I know that angle A is 55 degrees. And because these are parallel lines, I know that these are consecutive interior angles. So if they're consecutive interior, they must add up to 180 degrees. So 55 degrees plus whatever measure angle B is should equal 180 because they are consecutive interior angles. So let me go ahead and solve this little thing here for you. The amount for angle B would equal, in this case, let's see here, 125 degrees. Okay, so measure angle B would be 125. And finally, if we're looking for measure angle C, we have a theorem that says opposite angles of parallelograms are congruent. So I know that angle C and angle A must be congruent. If I know angle A is 55 degrees, then angle C must also equal 55 degrees. Okay, so if you're good with your parallel lines and you were good at that stuff, this should be a piece of cake for you. If you need to brush up, then we're going to brush up a little bit. Now we also have some theorems about diagonals, and these are the ones that are a little harder to remember. Okay, when we've talked about the relationship between transversals and parallel lines, and once again, it's the same kind of deal. It's something we've talked about, but now we're going to apply it to a specific figure. If we have a parallelogram, its diagonals bisect each other. So what it's saying is that in my parallelogram, I have these two pairs of congruent sides that are also parallel to one another. And when we make the diagonals, which is connecting this vertex to this vertex, and we're connecting this vertex to this vertex, the other diagonal, the distance here is the same as the distance here. It's getting bisected. And the distance here is the same as the distance here. So make sure you mark on your diagram what it's saying exactly. Okay, because the statement might not be as easy to follow as it is to see it in a diagram. Okay, so the diagonals bisect each other. That's going to be important. Also, with diagonals, each one separates the parallelogram into two congruent triangles. So if I made a diagonal here, I would know that triangle ABD and CDB are congruent triangles. That's really important. That's going to be a big one. Okay, we have congruent triangles in our quadrilaterals. So if I made this diagonal right here, there's lots of things we know now. This and this are equal. This and this are equal. We know that A and C are equal, D and B are equal. We also know that this one, we have two congruent triangles. It would be this guy and this guy. Okay, so our diagonals will separate it into two congruent triangles if we are using our diagonals to in a parallelogram. Be two congruent triangles. So once again, I have QRST as a parallelogram, so that guarantees me that this is parallel to this. This is guaranteed to be parallel over here. And it says find the indicated variable. Okay, these appear to be diagonal, so once again, I can mark these as being the same length. I can mark these as being the same length. I know that these guys across from one another are the same length, and these guys across from one another are the same length. I even know that this entire measure is equal to this entire measure, but I'm going to come back to that here in a second. Okay, let's first start with let's go ahead and try to find what x is. Where's x at? Where's the x variable? X. Oh, right here. That's 5x. Okay, its relationship can be found across the map, right all the way across, straight across. I know that 5x should equal 27. Because it's a parallelogram, they have opposite sides are congruent. So if I'm trying to find x, I know x equals 5 and 2/5. Or 27/5 would be fine. It's an equation technically, since we're using a unit of measurement, a mixed number would be better. So it would be 5 and 2/5 units long. Y is found on these two portions of the diagonal. Now, because these are both diagonals, I know that it was split perfectly into two pieces. So I know that 2y minus 5 must equal the y plus 4. If I subtract y from both sides. And I solve. I know we're pretty good at the algebra. Y equals 9. So in this case, I know y equals 9, x equals 5 2/5. And finally, if I need to find z, now z is going to be a little trickier. Okay, what I know about z is that this whole angle right here is equal to this whole angle right here. Okay, and so unfortunately I don't know how much this is, but I do. If you think about it here, I know that these, if I'm looking at these parallel lines, RS and QT, that I have a transversal here. And in that transversal, what I actually have is this 95 is actually an alternate interior angle with this. So I know this is 95 degrees as well. So total, I know that this guy is equal to this guy. I can also say that this 33 degrees is alternate interior with this 3z. So I'm going to actually set 3z equal to 33. It's just a big parallel lines problem at the end of the day. Z must equal 11. All right. So we've learned some theorems about parallelograms. Mostly they're repeats. They're just a different way of saying it, and we're applying it to a shape. But we have actually learned some new rules about diagonals. The last thing I want to talk about today has to do with the midpoint theorem. And I know we haven't done the midpoint theorem, but I think it'll make sense pretty quickly for you. It says determine the coordinates and the intersection of the diagonals of a parallelogram. I'm just going to draw a sketch. I don't really need a sketch to solve this problem, but I'm going to draw one so we have a nice visual. There's negative 2, 4, 3, 5, 2, negative 3, and negative 3, negative 4. Okay, so there's my F, G, H, and J in my parallelogram. So they're guaranteeing me that the slope between these 2 points is the same as this slope, as well as these slopes as well. Okay, so it's just a sketch. These are parallelograms, so I know these are equal, congruents, as well as parallel. And what it wants me to do is it wants me to find the intersection of the diagonals of a parallelogram. So what we need to do, we think, okay, well, I got this going this way and this going this way. I need to know what this point is right here. Okay. The midpoint formula is actually going to be this new formula we're going to use to find halfway in between 2 points. So in this case, what I need to find first is halfway in between F and H. Okay, and it doesn't matter which 2 points I find the midpoint of, because they're going to intersect exactly at the midpoint either way. So I need to find the midpoint of F and H, or I can do a different color. I could find the midpoint between G and J. It should be the same midpoint, but let's just check it out. Let's do F and H first. I'm doing F and H. I'm doing the midpoint of these points, these 2 coordinates. So F is negative 2, 4, and H is 2, negative 3. Now you may have done this in algebra, I guess. I'm going to use the first x and the first y, the second x and the second y. Those are subscripts, not exponents. So it just keeps our x's from being mixed up. And I'm going to plug them into the formula here. And basically this is saying halfway in between. That's why we're dividing it by 2. We're finding the total of the x coordinates and dividing it by 2, total of the y coordinates and dividing it by 2. That'll be the midpoint, which would make sense. It's like an average. So when I add the x's together, I get negative 2 plus 2 divided by 2. And when I add the y's together, I have 4 plus negative 3 over 2. So my sketch actually looks pretty accurate. So my midpoint is actually going to be at 0 divided by 2, comma 1 divided by 2, or in this case, 0, 1/2. Okay, that's what I'm going to say that this point is. Now, technically, where they intersect should be at the same spot. So I'm just going to double check that with these other two, the halfway point in between G and J, because that's what I'm looking for. I'm looking for the intersection of the diagonals. So let's do that. Again, this is x1 and y1, my second x and my second y. I'm going to just find the average of the 2 coordinates. So 3 plus negative 3 is 0 divided by 2. 5 and negative 4 is 1 divided by 2. Once again, I get the same coordinate, 0, 1/2. That is my actual intersection of my diagonals. It's halfway in between each of these points. Okay, so that's it for today. We learned a mid-segment, or we learned a midpoint theorem. We learned some theorems about parallelograms as well as theorems about parallelograms diagonals. That's it for today.